So, good afternoon. Welcome to the NPTEL live session of week 7 on BioMEMS and Microfluidics. The course instructor for this course is Dr. Shanthanu Bhattacharya, and this live session is handled by myself, Sabareesh. And to say about myself, I am the PhD scholar and the Prime Minister's Research Fellow, the Department of Mechanical Engineering at IIT Palakkad. And I am working in the research area of passive cooling applications. So this 1 hour live discussion, as you know, it's actually a glance through the weekly video sessions. Then we will discuss some Q&A or the problem solving part. Then if there are any doubts or queries, we can clear that and move on. So in the week 7, you might have, I hope you have gone through the lecture videos. So in that, the basic topics covered are the basics of fluidics and microfluidics. Then comes the stress fields and the terms related to viscosity. Then an introduction to non-Newtonian fluids, or the fluids which are non-Newtonian type. Non-Newtonian type. So do not obey the Newton's law of viscosity. Then the topics of flow over an infinite plate and the types of flow are discussed. Then the basic fluid kinematics parts were discussed. So I hope that the sessions were very clear to you, and if you have any doubt, we can clear that today. So let us quickly revise or just have a brief look at the week 7 topics, some important topics. The first topic was related to cyclic voltammetry, and it means that the cyclic voltammetry is a type of potential dynamic electrochemical measurement technique. Okay. And please note that it's a potential dynamic electrochemical measurement technique. And in cyclic voltammetry, as the name says, it's a cyclic and volta, or the potential measurement. And the metry means the measurement using the cyclic approach or the cyclic experiment by providing an input cycle. And the working electrode potential is ramped, or the input type is a ramped type input. And it is given as a linear function of time. So in general cyclic voltammetry, we give the working electrode potential as a ramped linearly versus time. So you should understand that unlike in linear sweep voltammetry, after the set potential is reached in a CV experiment, the working electrode or the potential of the electrode is ramped in an opposite direction to return to the initial potential. So it will be given a cyclic ramping or a cyclic way of input, and it will be brought back to the initial state in a cyclic method. And these cycles of ramps in potential may be repeated as much as times as needed. So that also may be noted. So it's actually a measurement technique to determine the potential measurement technique. And the current at the working electrode is plotted versus the applied voltage. You can see here one image to have a better understanding, to give the cyclic voltammetric trace, voltammogram trace. So like we see in angiogram or a kind of other measurement plots, ECG, electrocardiograph or electrocardiogram. This is a voltammogram. It's a variation of current which is in the scale of anyways in the microampere range and potential in volt. So this is for an AgCl type of electrode electrolyte combination. So the obtained curve is as shown in this. So initially it will be having a smooth curve, and IPC is the P cathodic and IPA is the anodic current. So they are opposite. That's why they're coming on the both sides of the x-axis. So this is for a reversible type of reaction. So a ramped type of input is given to it, and the voltage is the voltammogram trace is obtained, so that we could study about the performance of a particular kind of electrode electrolyte type. So why it is used? As I said, it's electrochemical properties of an analyte in a solution or a molecule that is absorbed can be studied. So that is the importance of cyclic voltammetry. Please understand that it is generally used to study the electrochemical properties of an analyte in a solution or a molecule that is getting adsorbed onto the electron. Here we can see it's an AgAgCl. So such type of absorbed reactions can be studied with the help of this cyclic voltammetry technique. That's it. So another concept that had been discussed previously, these are all related to the basics of the fluid dynamics. So these are very simple topics which you can understand and go through. So first topic that had been discussed was the concept of streamlines. So what are streamlines? So streamlines are a family of curves. Please understand that family of curves, and they are actually imaginary curves. Imaginary curves. Why they are used? They are used to connect those tangent vectors which are actually with the velocity field of flow. Suppose a flow is happening like this. You can see here a streamline for a car. So the streamline flow is the tangent, the direction of the tangent vector down to the velocity, particle velocity at every point. So these show the direction in which a massless fluid element will travel at any point in time. Suppose a fluid element, maybe an air fluid, air. So it is traveling along this time. So it gives the direction of the motion of the fluid. So if the flow is more streamlined, there will be less drag on this vehicle. So the designers or the manufacturers tend to make the design of the vehicle, even if it is a kind of a vehicle or if it is a kind of an aerofoil in an aeroplane, they will try to tend to make that design such that it is obtaining a streamlined flow. So in case if it is not a streamlined flow, it's a kind of a change of a flow, then there will be vortices or the flow obstructions happens, and that will create more drag on the vehicle, and it is going to definitely obstruct the free movement of the vehicle. So that is the streamline understanding. Another kind is a streak lines. So these are all parameters to identify the motion of a fluid particle when it is flowing through a fluid flow domain or a fluid flow type. So streak lines are the loci. Loci is the plural of locus, or all the points connecting the fluid particles that have passed continuously through a particular spatial point in the past. Suppose we are keeping a point here and we are analyzing the loci of all the fluid particles that have passed through a particular point. Suppose like this. A particle A is coming from here. It has passed through this, say this is C. Another particle B has come. Another particle D has come. So they have all passed through these point C. So now we are analyzing the path of all these particles, and these are called as the streak lines. So it is the loci of the points of the all fluid particles that have passed continuously through a particular spatial point in the past. Suppose another point, another part of fluid element comes from here, F, and it has gone through this way. So it has not passed through the point C. So it is not a part of these streak lines. Only A, B, and D have passed through the point C, and the loci of all particles that are passing to the point C will be analyzed, and that will give us the direction of the streak lines. So how is it studied experimentally? A dye or a colored substance will be steadily injected into the fluid at a fixed point extends along a straight line. Suppose we are conducting a fluid experiment and a flow is happening like this. Now at some particular point we are injecting a color dye. What will happen? These fluid particles will absorb the color and it will form a line here. So that lines are called the straight lines. So streamline, straight line, next comes the path line. So what is a path line? They are the trajectories or the path profile that individual fluid particles are following. So, so this can be understood as a, unlike from the previous, This is actually a recording of a path of a fluid element in the flow over a certain period. Suppose I am analyzing not three particles, A, B, D, we have analyzed in streak lengths, but I am not considering A, B, D, or F. I am just analyzing A. So what is its path along the fluid flow? That is what is path line is. So the direction the path takes will be determined by the streamlines of the fluid at each moment in time. So that is the meaning of the path line. Next comes the timeline. Timelines are the lines that are formed by a set of fluid particles that were marked at a previous instant in time, creating a linear curve that is displaced in the time as particle move. So that is with respect to a time period. So it is the analysis of the fluid particles that are marked at a previous instant of time. Suppose at t equal to 0 we have analyzed, then another point of time we are analyzing. So the motion of the particle at each instant of time maybe. So that is called as the timeline. So these are all the different parameters to identify the flow of a fluid in a particular domain or a experimental condition. So please understand that at steady flow state, all these streamline, streak line, path line, timeline will be equal. So that is what is the importance of a steady flow. Steady flow means at a particular section, if you are analyzing, the parameters that you are analyzing are going to be constant with respect to time. I hope that it is clear. Okay, next we can discuss about the classification of non-Newtonian fluids versus Newtonian fluids. So please have a look at the curve of this is the Newtonian fluid. What is a Newtonian fluid? The expression for Newtonian fluid is shear stress is directly proportional to shear strain. I mean the velocity gradient, not the shear strain, it's the velocity gradient. Sorry, it's the velocity gradient. So by eliminating the proportionality, we will put k into du by dy. This k is the coefficient of viscosity, mu. That is given by the Newton's law of viscosity. So all fluids which are obeying the Newton's law of viscosity are called as Newtonian fluid. So what are the non-Newtonian fluids? So it is not linearly proportional. Du by dy raised to n. Or we can generalize it as a into du by dy the whole raised to n plus b. If b equal to 0, a equal to 1 and n equal to 1, what are we getting? We get a equal to mu, then we are getting the Newtonian fluid type. Okay, so that is shown here. Next comes a non-Newtonian type of the dilatant or the shear thickening substances. So that is the dilatant type. So what are they? With respect to the shear stress, it is going to get thickened, it becomes more thick. So such fluids are called the non-Newtonian dilated or the shear thickening. For such fluids, this parameter n is greater than 1. So it's a rising curve. Next comes the non-Newtonian shear thinning type, like some of the we can say so some of the type of the ketchups or the kinds of non-Newtonian fluids, maybe concrete or several other types, they are shear thinning type. So for such fluids, n is less than 1, so it is a decreasing curve. So next comes the ideal Bingham plastic. So ideal Bingham plastic, it is, you can see here there is a minimum shear stress. So a minimum shear stress is required to bring it to the state of motion or the initial state. So it can be written as A into du by dy plus b. So n is actually 1, it is linear. So m into du by dy plus tau mu. That is the ideal Bingham plastic. Then the non-Newtonian plastic is there. So that's another kind where you can get the kind of plastic behavior. It's a non-linear type. So n is variable. So that are the classification of the non-Newtonian fluids. Another concept that had been discussed was the turbulence for the compressible and the non-compressible flows. So what is a turbulent flow? In fluid dynamics, turbulence or turbulent flow is a fluid motion which are characterized by the chaotic changes. Okay, so they are characterized by the chaotic changes in pressure as well as the fluid flow velocity. In a laminar flow, we know that it occurs when the fluid flows in parallel layers. So we can see the fluid flows in parallel layers in laminar flow. So that is a very ordered flow. But then the fluid flows randomly, these are called the turbulent flows. So it is a kind of a chaotic or non-ordered kind of a chaos flow that is happening, and there is a rapid changes in the pressure and the fluid velocity. So it is not going to be constant, it is variable. And several other parameters or the effect of drag or the kind of adverse effect of velocities or tendency to slow down, everything can happen here. So laminar can be thought of as an ordered kind of velocity, while this kind of turbulent flows are non-ordered or the chaotic kind of velocity. Okay. So how can we predict the onset of turbulence? Like when does a fluid flow turns out to be turbulent? So that is actually determined by the dimensionless Reynolds number. It is Reynolds number, it is rho b d by mu. So Reynolds number determines whether the flow is laminar or turbulent. So it is actually the ratio, can be thought of the ratio of kinetic energy to viscous damping in a fluid. So what are the forces in a fluid flow velocity? Fluid flow. So when a fluid flow is happening, there will be a viscous force acting between the layers of the fluid. Viscous force will be acting between layers. Then there will be a driving potential of the pressure which is causing the flow. So due to viscous force, they will be acting tangentially. So the fluid layers will try to resist. But fluid is a kind of, the definition of fluid is such that, what is a fluid? A fluid is any substance that deforms continuously under the effect of shear stress, how small the stress may be. So what differs from a solid from a fluid is the fluid can't resist a kind of a shear stress. It will continuously deform, even if the small the shear stress is. That's the proper definition of a fluid. Okay. So turbulence is actually created a lot of problems in the experimental as well as the physical analysis. And the interactions happening with the turbulence is a very complex phenomenon. Even Richard Feynman has described turbulence as the most important unsolved problem in classical physics. So even though we try to study this, there are still problems of obtaining the exact mechanisms or solving the turbulence problem in the classical physics problem. Okay. So we can also understand what is a compressible versus an incompressible flow also. So what is a compressible flow? When is a substance said to be compressible? It's very, it's then when it is incompressible means we can't do anything, the deformation. Okay. So the fluid element also undergoes a kind of deformation. So fluid element also undergoes a kind of deformation. So the compressible means its density change happens. So when can we treat a flow to be incompressible? So the change in density or the delta rho is very negligible. So how much? So according to the experience, we can treat that to be less than 10%. So if we analyze the fluid element or something, suppose the change in the density of the element with respect to this pressure effect, delta Py into 100 is less than 10%. We can treat them to be nearly incompressible flow. Example, fans, airflow through pipelets, etc. So where the compressible flow is not happening. So where does this compressible flow actually happens? In hypersonic flows or the flow at very high velocities. So the pressure is going to create a large effect on the fluid element. So it will be subjected to deformations, it will be subjected to the pressure variations and many of. And so what happens? So essentially at high flows, the parameter that is used to identify is the Mach number. What is Mach number? It is the velocity of the fluid to the velocity of the sound. So we are referring that to a particular parameter called as Mach number. When we say hypersonic condition, where hypersonic flight, even jet aircrafts, all the parameters or the type of the jet is characterized by this parameter known as Mach number M. So sound is the reference velocity. Velocity of the sound is the reference velocity. So that determines the importance of the density changes for the compressible fluids. Okay. So as a rule of thumb, we can treat when the Mach number is less than 0.3, the fluid flow can be assumed to be incompressible. Okay. So then the fluid flow can be assumed to be incompressible flow. So the reference condition is this. So that when the fluid velocity is or it is changing with respect to velocity of the sound, we can see that the Mach number comes into the play. Then the flow cannot be treated as a incompressible flow. Even the jet aircrafts, we refer to them as supersonic aircrafts or the subsonic. Subsonic is the Mach number less than 1. Supersonic greater than 1. So when a combustion happens in a nozzle, what happens? The air fuel mixture will be passing through the nozzle. So it will be subjected to a condition of Mach numbers greater than 1, equal to 1 and less than 1. Throughout it will be like this and finally it will change it into the higher Mach numbers to get the condition as this. So we can see also some kinds of diffuser, which is just the opposite of a nozzle. So there the reverse effect happens. So this is happening when the pressure and the velocity changes cannot be neglected. Okay, I hope that it is clear. Next, another topic as a flow, when you are studying fluid flow, the essential and the most foundation stone of fluid is based on these simple equations. So even the solving of this equation is a millionaire problem to obtain an exact solution for the various equations. So we can see here I have included just the continuity equation. This is the simplified version of the continuity equation for a steady state flow. Del dot V is 0. So what is del dot V? Del operator is the operator dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap into V. If V has got three components ux I cap, uy j cap, uz k cap, we can see here taking the dot product dou ux by dou x plus dou uy by dou y plus dou uz by dou z equal to 0. So that is the continuity equation in three-dimensional coordinates. Suppose a fluid is flowing in a horizontal direction and it has got no uy, uz, then the equation simply reduces to dou ux by dou x equal to 0. So this is a case of a steady state incompressible flows. Density remains constant. This is a simplified version of the Navier-Stokes equation. It's not a general equation, the continuity equation. So Navier-Stokes equations are generally based on the momentum equations. Okay, so they are essentially based on the momentum equations. So they are basically based on the momentum equations. So we can see here the momentum equation. This is the material derivative. This is called as a material derivative. Okay, so this can be expanded as dou v by dou t plus v del v operator, and each of these terms are representing each of the forces. So this is the pressure gradient, this is the body force, and this is the diffusion term or the viscous term. Okay, can you hear me? Okay. Okay, so the left hand LHS is, you can see here, it's equivalent to the, can be thought of equivalent to our convect. It has got two parts. One is a time variation of the temporal term, which means the velocity, when it is velocity is varying with respect to time, it will account that. And here we can see here the convective term. And this is the pressure gradient and the body force and the diffusion of the viscous terms. So this is essentially can be imagined or just visualized like sigma F equal to ma. So the all the forces are accounted in this direction. The LHS represent this condition. Mass into acceleration term. So this is actually the total acceleration term. Can be thought of acceleration of the. Okay, I hope that it is clear. Okay, now let's move on to the Q&A part. So the first question, for transient flow, the value of Reynolds number vary between. So what is Reynolds number? Reynolds number is rho into V into LC by mu. What is LC? LC is the characteristic length. Characteristic length. What is characteristic length? It may be the length or the diameter. If it is a pipe flow, we will take diameter. If it's a through a flat plate, we can take it to be. Rho is the density, V is the velocity, and mu is the coefficient of viscosity. So the question is transient flow. So we know laminar flow. For laminar flow, through a pipe or something, generally it's through a pipe. Please understand that this is a pipe flow. So in the case of a pipe flow, R equal to rho V d by mu, and that has to be less than 2300 to be laminar. If it is in a flat plate or a flow over a flat plate like this, then RE, yes, so then there is a transition region happening, then there is a laminar flow happening. So for laminar flow, it has to be less than 2300. Then comes a transition region. Then comes the turbulent region. So in our question, it is asked for the transient flow. So for transient flow, it has to be between 2300 and 4000. So please put these values. The correct answer is option B, 2300 to 4000. Next question, if the Reynolds number is more than 4000, the flow in the pipe will be considered. So it's just a continuation of the above. If R is greater than 4000, then it will be considered as turbulent, the chaotic. So the answer is turbulent, option A. When you can observe this turbulent flow, if it's a flat plate, a fluid flow is happening. Then there will be a transition region. Then comes the turbulent region. So in turbulent region, there will be a lot of vortices or the rotational flows happening. Whereas in the laminar region, it will be on the fluid velocity vectors are parallel, and so this is a so I hope this is understood. Move on to the next question. So which of the following property defines the internal resistance of a fluid? Option A, wettability, option B, viscosity, option C, friction, and option D, none of the above. So what is resistance? Resistance is the obstruction to the flow. So is wettability a property? It cannot be considered as a fluid property. Yes, it's not a characteristic of a, so it is not an option. And friction is not a property of the fluid. So only possible option is viscosity. So what is viscosity? It's a fluid property due to which there will be resistance between fluid layers. Suppose we rub a hand with each other, we know that there is resistance created. Similarly, when a fluid is flowing, the weight of the fluid or the fluid which is above, it will be pressing, and that will be directed by a velocity when the flow is happening. So for a fluid at rest, this viscosity is not doing anything. So when the flow is happening, the fluid flow property, so it's a flow property actually. So when a fluid is flowing through a surface or through a layer of another fluid, there will be definitely a resistance or a friction happening between them, and that is accounted as viscosity. So this expression for this is actually provided by Newton. He describes this as F is equal to, suppose if mu is the coefficient of viscosity and A is the area of cross section of the fluid flow, and F is equal to mu A into du by dy. Du by dy is the velocity gradient between the layers. Suppose if the flow is happening over a flat plate like this, then what happens? Suppose this is plate is fixed, so it is u0, and here the velocity is say 15 or some or a v value. Then what is velocity gradient if h is the height of flow? Is du by dy, which is v minus 0 by what is y? Y is h, so it is simply v by h. So Newton told that this is mu a into v by h. It is understand. So if we bring this to here, by so answer is option B, viscosity. Next question, when the temperature of a liquid increases, then what happens to the viscosity? So what is viscosity? Yes, so viscosity when the temperature is increasing, then what happens to the viscosity? So it's a fluid property. So with respect to liquids, as temperature increases, the viscosity comes down. Because as you can see here, if we start to heat suppose a lubricant like an oil, if you start to provide heat, you can see that it will flow more smoothly than a fluid at a room temperature. So what has actually happened? The friction between the fluid layers has decreased. So there the viscosity or the mu has decreased. So you can see that mu is a function of temperature. So for the case of liquids, it decreases. But please understand, in case of gases, as temperature increases, viscosity increases. Why that is? Because fluid is in a gas is composed of more loosely packed molecules of air or something, suppose a gas. So there is no the velocity gradient we can't estimate properly like in a fluid. What happens when the temperature increases? By Boltzmann's law, we can know that as energy of the fluid increases, K3 by 2 kT. That equation you can see acid. So the molecules start to gain energy, and what will they do? They will come and collide with each other. Okay, so there is total chaos inside as temperature increases. So what will happen? Between the fluid molecules, the friction has started to increase. So in gases, as the temperature increases, viscosity increases in most of the ideal cases. But in fluids, that molecules are tightly packed, so there is the point of random collision. It is actually happening a decrease in the viscosity or the fluid resistance between the layers. Okay. Next question. A liquid enters a pipe of diameter d with the velocity v. What will be the velocity at the exit if the diameter reduces to 0.5 d? So let us look. A liquid enters a pipe of diameter d. So a liquid is entering pipe of diameter d, and the diameter decreases to a height of 0.5 d. We need to find the velocity at the exit if the diameter reduces to 0.5. So this is a case of a fluid flow problem which makes use of the continuity equation. And that is actually derived from what is called as a Reynolds transport theorem. The derivation is not out of the scope. So the simplified for a continuous flow, we can simply write the product of density into area into velocity is constant. Suppose at section 1, a fluid has entered. It is exiting at another section 2. So if the fluid has a density rho here and the area of cross section is A here and it is V here, suppose A1, rho 1, A1, V1. At section 2, if the density is rho 2, A2, V2, we can write rho 1, A1, V1 equal to rho 2, A2, V2. Okay, so this is for an exiting flow. Please understand. So this is for a single unidirectional flow. When we take, we can write like this. Okay. So with that, if we look at this, the density of the fluid is assuming not to be changing. So what we can write simply A1 V1 equal to A2 V2. If we consider this section as 1 and this section as 2. So what is A1? It is pi by 4 into D1 square. If it is a pipe into V1 equal to what is at the outlet pi by 4 into 0.5 D the whole square into V2. So what we need is V2. So V2 equal to D1 square by 0.5 D1 square or D square into V1. So D1 is given as D, V1 is given as V. So what is the answer? This one is 0.5 square. So that is answer is 4. Yes. Okay. So answer is 4. So we need to understand that equation rho 1 A1 V1 is equal to rho 2 into V2 for a uniaxial or a single channel flow. Next question, it's two pipes each of diameter D converges to form a pipe of diameter 2D. Liquid flows with the velocity of V1 and V2 in two pipes. What will be the velocity of the third pipe? So here the case is one pipe is like this. Its diameter is given to be D. And it converges to form another pipe is also here. And they now converges to form another pipe of diameter 2D. So this is having a diameter 2D. So fluid is entering from here and exiting through here. So this is one section, this is second section, this is third section. So unlike in the previous, there are 3 sections. Now how we will analyze. So when there are multiple cases, you need to understand that. Just remember this: sigma rho I AI VI is 0. It is similar to the previous one. Suppose there are 2 sections, right, equal to 1 to n. So what is this? In the previous, if there are 2 sections, we will write rho 1 A1 B1. Because the fluid is entering, right? It is entering. And in the second session, the previous one, suppose in that at 1 it was entering and 2 it was in. So it will be minus because sigma is the algebraic sum. Rho 2 A2 V2 equal to 0. Or rho 1 A1 V1 equal to rho 2 A2 V2. Which we have written rho AV equal to a constant. So in this case, we can simply write this as sigma rho I ai bi equal to 0, where I varies from 1 to 3. So if we look at that, for 1 and 2 it is entering, 1 and 2 it is entering, at section 3 it is leaving the channel. Similar to a circuit analysis, so electrical circuit analysis. So if we look at that, we can see rho 1 a1 b1 plus rho 2 a2 v2 minus rho 3 a3 v3 equal to 0. So what we need, what we have, rho 1 is not changing. So rho 1 equal to rho 2 equal to rho 3. A1 is changing, A2 is changing, A3 is changing. So what is A1? A1 is A1 V1. We can simplify this as A1 V1 plus A2 V2 equal to A3 V2. So V3 equal to A1 V1 plus A2 V2 by A3. So A1 is proposed pi by 4 d1 d square v1 plus pi by 4 d square v2 whole divided by pi by 4 into 2d the whole square into v2. So here only 8 is required, so we can like that. So we will come to v1 plus v2 the whole by 4. So the correct answer is v1 plus v2 by 4. I hope it is clear. Next question, which of the following forces originate surface tension? So surface tension, we know sigma is equal to, how is it? The surface tension force we have determined sigma into cos theta by r. So the surface tension is proportional to the coefficient of surface tension, the angle of contact, and the radius of contact. So why is it happening? At the fluid flow interface, suppose like in a capillary rise, the fluids are very much attracted to each other. So what are cohesive forces between fluid of the same type? Adhesive forces between fluid and solid, or a different type, or another fluid type, different type of substances in interaction. So that is what is cohesive force is. So this surface tension is created, or the meniscus is created, how? Due to the cohesive force. So option B, only cohesive force is correct. Okay. Next question, the shear stress at a point in a liquid is found to be 0.03 Newton per meter square. The velocity gradient at that point is 0.15 per second. What will be the viscosity? So the shear stress is given to be 0.03 Newton per meter square. Velocity gradient du by dy equal to 0.15 per second. Please note the unit. So we have previously seen F is equal to mu A into du by dy, or F by A is equal to mu into du by dy. What is this F by A? That is actually the shear stress. Suppose a fluid is flowing like this. So if the fluids are at rest with respect to different surface, then there will be shear stress which will be generated. This will be the shear stress. Perfect. So we can simply write tau equal to mu into du by dy. So what is tau is given to be 0.03. Mu is we need to find out. Okay. And du by dy is given 0.15. So what is mu is 0.03 by 0.15. So what is that value? Is 3 into 10 raised to minus 2 by 15 into 10 raised to minus 2. We can get cancelled. So we will find it is 0.2 Newton second per meter square. Okay. Our question is, what will be the viscosity in poise? So what is one poise? Please understand, one poise is 0.1 Newton second per meter square. So our answer is 0.2 Newton second per meter square, which is how much? Is 2 poise. So the correct answer is option B, 2 poise. I hope that it is clear to you. Next question. Two pipes, each of diameter D, converge to form a pipe of diameter D, capital D. What should be the relation between D and D such that third pipe velocity becomes double that of each of the two pipes? So as discussed previously, we are doing one pipe like this, another pipe like this. They are convergent to form another diameter D. This is D and this is D. What should be the relation between D and D? How should you design these diameters such that the pipe in the third here, if it is, this is pipe 1, 2 and 3, the velocity in pipe 3 should be double that of each of 2v1 is equal to 2v2. So as I said before, we can use the relation rho I AI VA is 0. So rho 1 A1 V1 plus rho 2 A2 V2. If you are assuming the rho 2 A2, if you are assuming the fluid to be entering from this, okay, then minus rho 3 A3 V3 equal to 0. Rho is country constant, we can cancel that. Now A1 is proportional to pi d1 square, we can simply write pi into pi by 4 into d1 square for d square into v1 plus pi by 4 into d square v2 is equal to pi by 4 into d square into v3. So cancel pi by 4 everywhere. So d square v1 and d square v2 here. So if we take 1 and 2 here, we can assume v1 equal to v2, identical pipes. Because if the diameter is going to be constant, density is not changing, v1 is going to be equal to v2. So it becomes d square. Suppose v1 equal to v2, v1 equal to, we can keep it to be v. So 2d square into v equal to d square into v3. It is given that v3 should be 2v. So 2d square into v equal to d square into 2v. So when you cancelling that, we will get d square equal to d square, or what's the value d equal to d? So the correct answer is option A, d equal to. Okay. Last question. Which of the following velocity profile shown inside the tube shows a fully developed laminar flow? So the fluid is entering from here with the velocity, so that is a constant velocity, and as really it enters is forming the cone. What is this cone actually? This is the boundary layer formed inside the tube. Okay. Now they gradually converge and it forms a profile like this. So fully developed laminar flow. So what is fully developed? Fully developed means the velocity profile is independent of the linear distance or the distance along the pipe. You can see here the velocity profile is changing with the if this is the x direction to a particular length, and after this particular length the velocity profile is going to be constant. So at any section if you take independent of x, that is going to be constant. So this region is actually called the hydrodynamic entrance length. So the boundary layer has formed and it converged here. So you can see that is the length here. Afterward, which the flow is the flow profile has turned out to be which shape? It is parabolic shape, and the profile is independent of that. Hereafter, from this line onwards, the profile will be constant. The profile is constant. So which of them shows the correct? Option B. So B is the fully developed laminar profile, and it is parabolic. We have seen the relation where it is, you can see r square minus r square. U is a function. U is some dp by dx into a constant into r square minus 1 minus r square by r square profile. Where r is it is dependent only on the pipe radius. It is independent of the horizontal length or the x distance. But these profiles are functions of x as well as r. So please understand that fully developed flow, the profile is parabolic for a pipe. Okay. So I hope that that's clear, and that's all the question discussion and this understanding of this week 7. And I hope it is clear. If you have any questions, you can ask now. So I hope that it is clear, and if you have any questions or any kind of doubts, you can always post in the discussion forum, and always we can discuss in the coming session of the week 8 also. So if you have any questions, you can post in the discussion forum and you can ask me in the next coming session on Saturday. So that will be our final session on the live sessions of the weekly discussions. So see you next week on week 8 live interaction. And thanks for your patient listening. Have a great day. Thank you.